Okay, I'm going to try to quickly go through the Chapter 10 practice test, Unit 10 practice test. So we're starting off here with 4 compounds, A, B, C, D, and we want to kind of start off by saying, okay, what do these look like? So boron, 1, 2, 3, fluorines. Boron does not do an octet, so it's going to be a trigonal planar. Okay, we have C, H2, F2. So we're going to get fluorine and fluorine, and hydrogen and hydrogen, and that's going to be kind of a sort of a tetrahedral shape. OF2, remember oxygen makes 2 bonds and has 2 lone pairs, so it'd be fluorine and fluorine, it'd be a bent shape. And CH3OH can have 3 hydrogens, hydrogen, hydrogen, and then an O and then an H. That's really sloppy, sorry. Okay, it's alcohol. So it has a polar covalent bonds but forms non-polar molecules. Okay, the only one here that's going to be non-polar is going to be the boron trifluoride, answer A. Okay, because those are going to be at 120 degrees, and that's going to, cancel out any bond polarity. Okay, has the largest bond angle around the central atom. Well, this would be 120. This would be about 109.5. This will be a little bit less than 109.5 because of the lone pairs, and central atom here again, that's steric number 4, so that's going to be about 109.5 also. So the 121, so again that would be answer A. So the both answer A is expected to have the highest boiling point. Okay, so who has the greatest intermolecular forces? Well, this non-polar molecule, that's not going to be any good. But we have over here, we have the CH3OH, okay, this guy, that's going to have hydrogen bonding. So hydrogen bonding, as far as molecules go, that's the strongest intermolecular force, so that expect that to be answer D. And has a steric number of 3. Okay, again over here, boron, okay, it's going to have 3 bonds coming out, 3 bonded atoms, no lone pairs, steric number of 3, so that's also answer A. Okay, down here, over here, 5, 6, 7. So here we have some new molecules, and these molecules, we have to kind of look at them. I'm going to clear off the ink here. Okay, so what do we have? We have NO2 minus. Okay, NO2 minus is going to be nitrogen, and after we do the nitrogen, then it's going to double bond an oxygen one way, single bond the oxygen the other way. We're going to have a lone pair, lone pair, lone pair, 3 lone pairs here, and there's going to be a resonance structure for that. So since we make the double bond one way, you can do it the other way. Okay, we should use brackets and a negative charge. I can't see my question anymore. Okay, so let's go back a little bit. Okay, CO2. We know CO2 is going to be a carbon with a double bonded oxygen, another double bonded oxygen, something like that. H2O, we know that that's going to be a bent molecule, HOH, and a couple of lone pairs on that oxygen. And HCO2H, and that one, we have to remember that that is an acid. So an acid would be C, double bond O, OH, and then over here would be an H off of that side there. So again, for each of these, you kind of need to know what they're shaped. You got to be able to draw these as you go. So now, the central atom has only 1 lone electron pair. Okay, and that looks like this guy here, the NO2 minus, because this has no lone pairs on this carbon. This has no lone pairs on that carbon. This has 2 lone pairs on that central atom. So it has to be answer A, the NO2, and that's on that one. Has a trigonal planar geometry around the central atom. Well, CO2 is linear. This guy is trigonal planar. H2O is tetrahedral. And this guy here is going to be trigonal planar, actually. So, has trigonal planar geometry around the central atom. I would say this guy would be trigonal planar because you have 3 atoms coming off at 120 degrees. This guy, the electrons are trigonal planar, but the molecule itself is only bent, so that's not the answer. So it has to be D, answer D. Is drawn with resonance structures. Okay, I didn't draw them, but this guy here had to have resonance structures because we made a double bond to one oxygen. We didn't do the others. We'd have to draw both structures. So that would be answer A, NO2 minus. And all bonds have a bond order of 1. Who's got all single bonds? Well, that's got double bonds. That's bond order of 2. over here, the H2O. Those two bonds are single bonds. So H2O has everybody has bond order 1. So that's answer C, H2O. Okay, section 2. Determine whether each description refers to covalent bond, ionic bond, or metallic bonding. So these are just facts. So we'll go through is involved in solids that conduct electricity. Okay, solids that can conduct electricity. Covalents cannot conduct. Okay, ionics only can conduct when they're either aqueous or liquid. So it has to be the metallic. And that's the right answer. Is found in molecular and network solids. Okay, so molecular solids are held together with covalent bonds. Like all these examples up here, they have covalent bonds holding them together. Okay, and the covalent network solids like diamond, those are totally held with covalent bonds. Form solids of alternating cations and anions, pretty obvious. Anions and cations are positive and negative ions, ionic compound. Found in copper, we should just recognize that copper is a metal, so it's metallic bonding. Found in magnesium chloride, we should recognize that that's Mg2 plus and Cl minuses, so that is going to be ionic compound. Forms between two nonmetals. We know non-metal forms covalent. Okay, metallic would be metal-metal, ionic would be metal-nonmetal. And held together by shared electrons between atoms. Okay, shared electrons is a covalent bond. Transfer of electrons is ionic bond. Sea of electrons or delocalized electrons is metallic bond. So shared between two atoms there is covalent bond. Next page. Okay, here's our favorite questions. Okay, so H2O has linear geometry? No. H2O is a bent molecule. We've seen that. It looks like a little Mickey Mouse, so that's a false. Because the oxygen in H2O forms two polar covalent bonds with hydrogen. That is true. Okay, we have H, we got O. O is one of our strong nonmetals. H is a weak nonmetal. So it is a polar covalent bond, so that's true. Okay, but that's not the reason. Anyway, so false, true is the answer. Second one, molecules of NH3 are expected to dissolve in water. Okay, NH3, if we draw that, it's going to be polar, because it's bent like this. And we've got nitrogen with hydrogen, which forms hydrogen bonding. Okay, water is also hydrogen bonding, so those two would mix really, really well. So it's true, it is expected to dissolve. Okay, NH3 is a polar compound. Okay, that is true. And because of that, it's going to dissolve in water, so we're going to call it TTCE. 18. Chlorine is expected to have a lower boiling point than HCl. Okay, chlorine, Cl2, Cl with Cl. Okay, that's going to be a nonpolar molecule. It's going to have LDFs. Okay, and that is the weakest of the intermolecular forces. HCl, okay, is not ionic. HCl is dipole, because it's the polar molecule, so DDI. And when we're talking about boiling points, okay, low boiling point, high boiling point means weak intermolecular force, strong intermolecular force. So we're saying chlorine has a weaker intermolecular force than hydrogen chloride does, DDI, and that is absolutely true because chlorine displays only London dispersion forces, while HCl has dipole-dipole interactions. We already said that, and that's true. And we know that that is stronger, so I would call that TTCE. Okay, go on to multiple choice. Which of the following is not a description of a sample of brass, an alloy of copper and zinc? Okay, well, we know that that's going to be a metal, so we know it's going to be a good conductor. We know that it's going to be malleable and ductile, probably going to be shiny. So which of the following is not a description of a sample? So who's not a metal? It's ductile and malleable. That's not the answer because that's good for metals. It is a lattice of cations surrounded by a sea of electrons. That's the classic definition. That's not the answer. It conducts electricity when dissolved in water. Okay, metals do not dissolve in water, but metal, you might be fooled. It says, yeah, metals are good conductors, but you don't dissolve them in water. And shiny and lustrous, okay, that is definitely a metal. So answer C. How many electrons are transferred when aluminum ion forms an ionic bond with phosphorus? Okay, well, if we look on the periodic table, we know that aluminum is in family 3, and it has 3 valence electrons. Phosphorus is in family 5, okay, and so it has 5 valence electrons. So the electrons 3 are transferred, and it's going to fill this guy's shell, and aluminum would, lose all of its electrons. It would be 3 plus, and this guy would be 3 minus. Okay, so 3 electrons are being transferred. Okay, which of the following best describes the NH bond in NH3? Okay, well, NH3, anytime N and H, they're both nonmetals, but nitrogen is one of the strong nonmetals. Okay, because remember the 4 strong nonmetals are NO, F, and Cl. So nitrogen is, hydrogen is not, so that's going to be a nice polar covalent bond. Polar covalent bond, certainly not an ionic bond. Okay, hydrogen bond is not even an appropriate answer here. And non-polar covalent, okay, definitely a polar covalent bond. Okay, 22. When calcium is bonded with oxygen, okay, we would expect that to be an ionic compound. So calcium and oxygen are in a sea of electrons. No, that's a metal. Calcium oxygen share. No, that's going to be a covalent. Calcium gains 2 electrons while oxygen loses. That's the right idea, except calcium is the one that loses. So, and oxygen is the one that gains. So that's this answer here, D. 23. When ice melts, which of the following are broken? Okay, so when ice melts, we're talking about H2O. And these H2Os are held together with covalent bonds. But when it melts, those covalent bonds are not broken. The little hydrogen bonds are broken. So we're looking for what is broken. Hydrogen bonds are broken, not covalent bonds, and there aren't even any ionic bonds. So the answer is 2 only hydrogen bonds. Okay, bonds between which of the following pairs of elements can be considered polar covalent? Polar covalent. So we're looking for a metal. No, we're not. We're looking for a non-metal and a non-metal, and we need one that's a strong non-metal and one that's a weak non-metal. So C and P, we can knock that out because they're both weak. H and Cl, that's good because Cl is one of our strong nonmetals, H is not, so that's the answer. Mg and N, that's a metal nonmetal, that's going to be ionic. And O and F, both of those are strong nonmetals, so that would be a nonpolar covalent as well. 25. Which of the following elements is expected to have the highest electronegativity? Okay, so if you can see our periodic table, we need somebody very far and very to the far and right and up, okay, and not the noble gases, and that's going to be oxygen. Okay, oxygen is the second most electronegative atom. The only one higher is fluorine. Which of the following is expected to have the highest melting point? So we want somebody that has the strongest IMF. High melting point means strong IMF. So these, we look at, these are all ionic compounds, So if we're doing ionic compounds, we want to look at the charge, and we want to look at their size. And a +2 -2 would be stronger than a +1 -1. And then if we find those, we'll go to size. So first one here is +1 and -2. Second one is +2 and -1. C is +2 -2. And D is +2 -2, so those ions. So it's definitely not A or B. Now these two, the larger it is, the weaker it is, okay, because the ions are farther apart. So O and O, we don't have to worry about that. Magnesium and barium, if we look on the periodic table, magnesium is toward the top, that's smaller, has fewer shells. So the magnesium oxide is the stronger IMF. Smaller size is a stronger ionic bond. 27. Which of the following electrons has the same number of valence electrons as phosphorus? Okay, just look on the periodic table. Who's in the same column as phosphorus? So nitrogen would be a good answer. Okay, antimony. Antimony, that's the one that's in the same family. The other ones are in different families. Okay, 28. In the Lewis dot structure for PF3, how many total lone pairs are drawn? Okay, so we have to kind of do this carefully. So here's a phosphorus, and it's got 1, 2, 3, 4, 5. Okay, it's going to hook onto a fluorine, 1, 2, 3, 4, 5, 6, and another fluorine, and another fluorine. Okay, so we have lone pair, lone pair, lone pair, lone pair, lone pair, lone pair. So on this guy here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lone pairs drawn. 1 on the phosphorus, 3 on each of the fluorines, and that makes 10. In the Lewis dot structure for SO, what type of bond is formed between S and O? Okay. Okay, Lewis dot structure. We don't even need Lewis dot structure. Okay, just in the compound of SO. Okay, well, S is one of our weak nonmetals and O is one of our strong nonmetals, so it's going to be a covalent bond, and it is going to be a, how do we say it? Okay, it's going to be a double bond, and it's going to be polar. Okay, so we know it's a polar covalent bond. Now, S and O. S, okay, has 6 valence electrons. O has 6 valence electrons. And in fact, this is going to be analogous to 2 oxygens, which is a double bond. And so we're going to put a double bond between them, and a lone pair, lone pair, lone pair, lone pair. And that's going to be the answer, because that's 2, 4, 6, 8, 10, 12 electrons. Now, if we were trying to draw SO, we might go back and say, you know, give everybody an octet, and take away a pair, make up share, come up with that structure. So S and O would be polar covalent, and it's a double bond, so the answer is D, polar covalent double bond. Okay, 30. How many single and double bonds are in a molecule of CH2O? Okay, it helps to kind of think back to the molecule, you know, when we built these, and see how would we put that together with the models. And we would have, remember, carbon can make 4 bonds. And so carbon can make 2 bonds to the oxygen and 1 bond each to the hydrogens. So this would be formaldehyde. And so what's the question? We're going to make how many single and double bonds are in a molecule. We have 2 singles, we have 1 double, and that is answer B. Okay, but to get that, you know, you have to remember this is the structure, and kind of think back to when we built the models. That might help a little bit. Okay, which of the following has a trigonal pyramidal geometry? Trigonal pyramidal. So trigonal pyramidal is something that's going to be like a pair of electrons there, and like a hydrogen, and a hydrogen, and a hydrogen. So something like that. So like ammonia is something that's trigonal pyramidal. You know, it's got a lone pair based on a tetrahedron. So BH3, you know, that would be trigonal planar. CH4, that would be tetrahedral. H2S would be bent. So it's PH3, which would be the same family as NH3. And that the answer. 32, what's the expected bond angle in O3? So again, we've done O3 a couple times, so you might want to kind of memorize that one. And when you get all done, it looks like this, and it would have a second structure, you know, where you put the double bond the other direction for ozone. And so the steric number is 3, okay, because you look at this, it has 2 bonded atoms, 1 lone pair, so that's a steric number 3, so basically it'd be like 120-degree bond angle. 33, which of the following molecules be expected to have dipole-dipole interactions? So we're looking for a polar molecule. So we can eliminate CH4, because CH4 is, you know, tetrahedral, very nonpolar. Okay, we can eliminate CO2, because we've seen CO2, and I would just memorize this structure, because you see it all the time. Okay, very nonpolar. Okay, N2, all their diatomics, they have to be nonpolar. Okay, HCl is a nice polar molecule, 2 different atoms. One is a strong nonmetal, one's a weak nonmetal, so it's polar, and it's going to have dipole-dipole interactions. Okay, which of the following solids is not held by intermolecular forces? So what it's really saying is which of these is not a molecule, which is not a molecular solid. And so hopefully you recognize A, that's silica. You know, carbon is diamond, carbon is graphite, and silica, SiO2. So that is not going to be held together by covalent intermolecular forces, held by covalent bonds. CO2 is a molecule, NO2 is a molecule, H2O is a molecule. 35, all the following form molecular solids except. So who's not a molecular solid? So we're looking for a metal, or we're looking for ionic, or we're looking for covalent network. And that's why answer A is the right answer, because that's an ionic compound. Okay, these are two nonmetals. That's not the answer. Sulfur, okay, that's not going to be it. And H2O, two nonmetals again. So those are all molecules. 36. Which of the following, which is solids of which compound expected to have the highest melting point? So again, here we want the largest IMF. Who's going to have the largest IMF? So we got to look at everything. We have HF, we have HCl, HBr, and HI. Now they all seem kind of similar, except HF is going to have hydrogen bonding, okay, whereas HCl, HBr, and HI are all going to be doing dipole-dipole and London dispersion forces. So HF has hydrogen bonding in addition to London dispersion forces, so that's going to be the strongest IMF, and that's going to be the highest melting point. Okay, finally here, okay, draw the Lewis structures for the following compounds. Okay, so here are all the pictures. So SF4, okay, S has 6 valence electrons. It uses 4 of them to hook on the fluorines, and it still has 2 left over, so notice those 2 are put onto that central atom. Okay, so the steric number of that would be 5. CO3 2 minus. Okay, if we got started, we'd put a C. We would give an octet to everybody. And then if we finished up our octets, then what we find out is that that's too many electrons. So we would have to do is take away a pair, make these share. And since we make a double bond one way, we'd actually have to make a double bond all the other 2 ways too. So that's why we end up with 3 different resonance structures for that. Okay, we have C2H4. If we started off and gave everybody an octet, we would find out we drew too many electrons. So again, we'd take away a pair, make them share, and we get a double bonded carbon-carbon double bond there. Okay, lithium fluoride, hopefully you recognize that that's ionic. Okay, it's lithium plus and fluoride minus. So we draw the 2 structures, the 2 ions next to each other, and that would be the correct resonance structures. Okay, and there's 2 points each. Now again, on this one, you would have to show the resonance or else you don't get the points. Okay, for 38, for each of the following compounds, identify the type of bond in the molecule, determine whether the molecule is polar, and write the strongest intermolecular force that exists in the solid. So lots to do. So the first one here, we can see it's carbon bonded to 2 sulfurs, very symmetrical. Okay, so the shape of that guy is going to be linear. Okay, steric number of 2. It's going to be 180 degrees, sticking straight out. Okay, nonpolar, because even though the bond itself might be polar, the whole molecule is nonpolar. And since it's a nonpolar molecules are LDFs, London dispersion force. Okay, the second one here, we have P with 3 BRs. That picture is correct. Okay, so we'd have trigonal pyramidal, because, you know, it's like a tetrahedral, but there's no atom on one end, so it's pyramidal. Okay, so the bond angles are going to be roughly 109.5. The lone pairs squeeze them a little bit, so 107 is a great answer. Okay, this is not correct on here. This would be a polar, well, okay, I would say, boy. Okay, because of the shape, I would kind of guess this is sort of a polar molecule, but these are both weak nonmetals, so the bond itself is not very polar. So saying that that's nonpolar, that would follow our rules. Okay, I think in reality, I bet if we checked it, it's somewhat polar. Okay, so if we're going to say it's nonpolar, then it's going to be London dispersion forces. So following our rules, we're going to say that that bond is not very polar, so it's a nonpolar molecule, and it's going to have London dispersion forces. Okay, SCl2, okay, that nice bent molecule. Okay, the bond angles, okay, probably, you know, about 109.5, but because of those lone pairs push things together, so about 104, 105 sounds reasonable. Okay, definitely a polar molecule, because Cl is a strong nonmetal, sulfur is a weak nonmetal, so it's going to be a polar bond. Okay, and since they have bent shape, it's going to make it a polar molecule, and dipole-dipole interactions. Okay, last one over here, COCl2. Okay, again, this might be easier if you think about the model. Carbon in the middle is going to double bond the oxygen, and chlorines on each side. Okay, steric number there is 3. 3 bonded atoms, no lone pairs on the carbon. So it's trigonal planar. Trigonal planar basically 120 degrees. Okay, carbons and chlorines, okay, are, well, chlorine is a 3.0, okay, electronegativity. Carbon is 2.5. Oxygen is 3.5. Okay, so I would actually say this is a polar molecule, okay, because of that carbon-oxygen bond right there. Okay, that's going to make this pretty polar because oxygen is 3.5, carbon is 2.5. I would say that's polar, and I would say that that's not London dispersion. I would really say that that is probably dipole-dipole interactions. Okay, so the chlorine parts would kind of even out, but I think that that oxygen is going to make it kind of a polar molecule. Okay, well, the oxygen would be kind of negative and the chlorines would be kind of negative, so all 3 edges be negative. So, oh boy, so that might be kind of nonpolar. Okay, it wouldn't be very polar because the 3 corners of it, are all going to be kind of equally negative. Even so, the oxygens are going to be more electronegative than the other 2. I would say it's going to be a weakly polar molecule. Okay, down here for CO2. Okay, CO2, draw the structure. So hopefully, I think you really got to kind of memorize CO2 because you see it all the time. Double bond, lone pairs on the oxygen. Okay, so the forces represented by the solid lines. Okay, the solid lines are the lines that are holding the C's to the O's. Okay, those are definitely covalent bonds. Okay, polar covalent bonds. And you have some choices down here which ones to pick. So covalent, but they're polar covalent because C and O, oxygen is a strong nonmetal, carbon is a weak nonmetal. Okay, the dotted lines, though, those are the intermolecular forces, and because CO2 is nonpolar, it's London dispersion forces. Okay, CO2 is a nonpolar molecule. Okay, just the fact it's a molecule makes it a molecular solid, and that's that answer. And then we have here some information, and we're saying that CO2, okay, has a melting point of -78. Actually, it doesn't melt, it sublimes. Okay, that's very, very, very low. So this has a really weak IMF. Okay, and the other one melts at 1600, which is huge. Okay, I mean, much hotter than you could get like on a stove or something. Okay, in fact, you have to like a kiln or something really, really hot. So that's a very strong intermolecular forces. Okay, explain why. And the reason why is because CO2, okay, is a nonpolar molecule held together with LDFs. And SiO2, we recognize that's one of our covalent network solids, silica. Okay, and so it's going to be held together with covalent bonds, which are much, much, much stronger. So you're going to have to heat this up much higher to get that substance to break down. So London dispersion forces, very weak, easy to break. Okay, covalent bonds, very, very strong. You have to really heat that up in order to get that to break down. So that's why those numbers are very, very different. And that is the practice test.